In this video, we'll discuss how to use the BJT as an amplifier and as a switch. We'll also talk about the phototransistor and its application. As we previously discussed, one of the applications of a transistor is an amplifier. It can amplify both AC and DC signals. A lot of the interesting real-world applications utilize AC signals, and it would therefore be wise and interesting to talk about amplification of AC signals. In our main reference, in order to distinguish between variables that represent AC and DC signals, you take a look at the subscripts. If the subscripts are capitalized, then we are referring to the DC signals. If the subscripts are in small letters, then we are referring to AC signals. For internal transistor resistances, small letters are used as variables to represent them. Please keep this in mind and use this nomenclature as well to avoid confusion and minimize mistakes. The figure that you're looking now shows the basic transistor amplifier circuit with an AC source voltage. Notice that the DC bias voltage VBB is superimposed on the AC signal as seen at the input or the base resistance RB. The capacitor of the AC signal connecting to the DC signal is a coupling capacitor. We say that the AC signal V sub S is capacitively coupled to the DC signal VBB. The coupling capacitor couples the AC signal to the input of the transistor, but prevents the DC signal to affect the input AC signal. At the input Vin, the AC signal is shifted upward as seen in the V versus T graph, and the shift corresponds to the DC signal. Keep this in mind. In our discussions, we'll talk only about the AC signal being amplified. The only effect of the DC signal is to shift the AC signal upward or downward in the voltage scale. The base voltage VB is just the voltage across the base emitter junction. The AC signal does not see the DC barrier voltage of plus 0.7 volts. Instead, it sees a small resistance called the internal AC emitter resistance, designated as R'E, and appears in series with RB. Thus, the AC base voltage is just a product of the AC emitter current and the internal AC emitter resistance. The base voltage is also related to the source voltage with the difference of the voltage across the base resistor. The AC collector voltage is just the AC voltage drop across RC. Since the emitter current is approximately the same as the collector current, we can also write the collector voltage in terms of the emitter current. The voltage gain is defined as the ratio of the collector voltage to the base voltage as shown. Since VC equals IE RC and VB equals IE R'E, then the voltage gain is just equal to the ratio of the collector resistance to the internal AC emitter resistance. Let's consider this example. Determine the voltage gain and the AC output voltage in the figure below if R'E is equal to 50 ohms. The voltage gain by definition is just RC over R'E. RC is equal to 1 kilo ohm and R'E is 50 ohms. Thus, the voltage gain is 20. The AC output voltage is therefore equal to the voltage gain times the base voltage. Since the base voltage is 100 millivolts and the gain is 20, the output AC voltage is 2 volts RMS. Let's now consider how to use the transistor as a switch. When the switch is turned off, the transistor is used in the cutoff region. If you recall in the previous video, the cutoff region is when the base voltage is 0, but the collector emitter voltage VCE is non-zero. As we previously learned in the cutoff region, VCE equals VCC. Thus, the transistor acts as an open switch so that when you measure the voltage across the collector and emitter terminal with a multimeter, you'll measure the voltage VCC. When the switch is turned on, the transistor is used in the saturation region. You put in a sufficient amount of base voltage to drive the transistor to saturation. Thus, in this case, the collector-emitter voltage is very small and modeled as a closed switch. The saturation current is just equal to VCC minus VCE saturation divided by the collector resistance. To determine the correct base voltage, you can determine the base current through the DC beta parameter. Let's again consider this example. For the transistor circuit given below, what is VCE when Vin equals 0 volts? If there's no input voltage, then VCE is just equal to VCC. Since VCC is equal to 10 volts, then VCE is also equal to 10 volts. What minimum value of IB is required to saturate this transistor if BDC is 200 ohms? Neglect VCE sat. We can solve for the IC saturation using the equation VCC minus VCE sat over RC. Since we are neglecting VCE sat, then IC saturation is just VCC over RC. So VCC is 10 volts and RC is 1 kilo ohm, which means that IC sat is just 10 milliamperes. We can now solve for the minimum value of the base current using the DC beta parameter. So IB minimum is equal to IC saturation divided by the DC beta parameter, which means that 10 milliamperes over 200 is equal to 50 microamperes. And this is our minimum base current. Calculate the maximum value of the base resistor when Vin equals 5 volts. If Vin is equal to 5 volts, then the base resistance or the voltage across RB is equal to 5 volts minus 0.7 volts. Now the base resistance is equal to the voltage across the base resistor divided by the minimum base current. So this is 5 volts minus 0.7 volts divided by 50 microamperes is equal to 86 kilo ohms. Thus, in order for this circuit to work, you need a base current of 86 kilo ohms, a base resistance of 86 kilo ohms, and you must drive the base terminal up to 5 volts to switch on the resistor. One simple application of the transistor as a switch is to use it for blinking LEDs, for example. A square wave signal is placed at the input of the switch. Let's now consider this example. The LED in figure 4-25, or in this figure, requires 30 milliamperes to emit a sufficient level of light. Therefore, the collector current should be approximately 30 milliamperes. For the following circuit values, determine the amplitude of the square wave input voltage necessary to make sure that the transistor saturates. Use double the minimum value of the base current as a safety margin to ensure saturation. VCC is equal to 9 volts, VCE saturation is equal to 3.3 volts, RC is equal to 220 ohms, RB is equal to 3.3 kilo ohms, beta DC is equal to 50, and VLED is equal to 1.6 volts. Let's first solve for the saturation current or the collector current. Originally, our equation is VCC minus VCE sat divided by RC. But since the LED drops a voltage, or there's a voltage drop across the LED, we must include that into the equation. The voltage drop across the LED is 1.6 volts. Thus, the voltage at the collector terminal of the BJT transistor is equal to VCC minus VLED minus VCE sat, which is 9 volts minus 1.6 volts minus 0.3 volts. If we divide that by 220 ohms, which is the collector resistance, we have a saturation current of 32.3 milliamperes. From the saturation current and the DC beta parameter, we can get the minimum base current. So 32.3 milliamperes divided by 50 is equal to 646 microamperes. In order to get the input voltage, we use this equation IB is equal to VRB over RB. Now the voltage across RB is just Vin minus 0.7 volts, and RB is equal to 3.3 kiloohms. We now rewrite this equation in terms of Vin so that we can determine Vin. Vin is equal to 0.7 volts plus 2 times 646 microamperes times 3.3 kiloohms. Remember that we are putting in a factor of 2 since we are required to use double the minimum value of the base current as a safety margin to ensure saturation. Thus, the input voltage required is 4.96 volts or 5 volts. So we must have a square wave with a maximum amplitude of 5 volts switching on and off every 1 second. And what this does, is that it switches on and off the LED every 1 second as well. The phototransistor is a variation of a BJT transistor, except that the base voltage is switched with a collector base PN junction that reacts to incident light. You can imagine that this PN junction is exposed. When there is no incident light, only a small amount of thermally generated current is present. In light applications and devices, this current is called dark current, or the current generated when there is no light. In the presence of light, a base current, I sub lambda, is produced that is directly proportional to the intensity of the incident light. The collector current also changes with the intensity of the incident light. The schematic symbol for the phototransistor is shown. Since there's really no need for the base terminal, most phototransistors only have 2 lead wires. In cases when there are 3 lead wires, the third lead or the base lead can be used as a conventional BJT with or without the additional light sensitivity feature. In a typical application, the phototransistor is connected in series with a collector resistor, RC, and the output is taken at the collector lead wire of the transistor. Typical collector current curves are shown for varying incident light intensities. You can see that it behaves exactly the same way as the BJT if we replace the base terminal with light as the input signal. It must be said that these phototransistors are sensitive to all light over a limited range of wavelength. It is most sensitive at specific wavelengths, particularly in the red and IR part of the electromagnetic spectrum. One application of a phototransistor is to activate a relay switch. A relay switch is just a switch that is turned on when current passes through a relay coil. In circuit A, the phototransistor Q1 is connected as shown to Q2 and is powered by VCC. When there's no light, Q1 is switched off and there's no base current to Q2. When incident light is present, Q1 is turned on and there is sufficient amount of current to turn on Q2. This increases the collector current which passes through the relay coil. The diode across the relay prevents current flow from the source to the collector terminal of Q2. In the second circuit in B, the relay is light deactivated. When there is no light present, the relay is turned on. This is because current is supplied to Q2 by VCC through R. When there's no current through Q1, since Q1 acts like an open switch. When light is present, Q2 then acts as a closed switch and current then flows through Q1 and there is a decrease of current through the base terminal of Q2. Q2 is then switched off and the relay is turned off. I hope you've gained some insight on a couple of fundamental applications of a transistor. Like we discussed in the previous video, even though these are basic applications, it is this basic principle that is being used in digital electronics. Your computer processor, after all, is nothing more than millions and millions of transistors switching on and off. In our discussions next week, we'll talk about biasing transistors and discuss in more detail how transistors are used as amplifiers.